Hey, this is Horner, and this is the last rotational dynamics free response problem. It is number 4 for the review. It says the diagram on the left. No, it's not on the left. It is on the right. So I changed that. Shows an apparatus that consists of a thin frictionless axis with several turns of rope wrapped around it. So you'll see the rope there. There are 2 handles. You can use the handles to apply a force in order to raise the object of mass m. So you're going to do a little bit of, you have a little force in order to turn this thing and make it go up. So the work here is equal, but the force that you use is a lot less. The diagrams below show several handle locations. They want to know which one would be the best in order to make this thing rotate, and you're grabbing onto the gray handle. They want to know which one will have the will do best in order to have the greatest upward acceleration. So to do that, we're going to pull straight down. That way you get to work with gravity. So to get the most torque, the handle needs to be set horizontal so the person can pull straight down. So notice now I've got a 90-degree angle here, and that will give it the most acceleration. If I did it here, nope, here, nope, and here, definitely not. So you'd have to go left. But here we've got that nice 90-degree angle, and you're using gravity to help you a little bit too. For letter B, another much taller student can stand next to the apparatus and easily exert a force of constant strength to one handle in order to raise the mass up with a constant velocity. The student observes that the handle she is holding moves faster than the rising mass, and the force she applies to the handle is much less than mg. So they want us in a paragraph to go through and explain why. We can use equations if we want to and refer to diagrams. So we know the tension, first point, tension is equal to mg, since that block moves with a constant speed. So that's easy. If the rotation has a constant speed, so this is super important, we know the torque in should be equal to the torque out. The force on the handle is less than the weight of the block because the handle has a much greater radius than the tension force radius. So if you go back up, you'll see that the radius here is super small compared to the radius that we have for the handles. And that's why the force on the handle is less than the weight of the block. So the speed of a point on a rotating object is proportional to the radius, and because that handle has a greater radius, it must be turned faster in order for that block to move up. So as you turn this quick, the block moves up very slow because it's got a small radius. And that is the end of question number 4 for rotational dynamics.